In this video, we're given a crown glass lens that's an index of refraction of 1.52, and we've applied an anti-reflective coating to it that's fluorite with an index of refraction of 1.43. And this time we're given the thickness of the thin film, that's 89.0 nanometers, and we're trying to calculate the wavelengths of light that will interfere constructively and destructively through this film. Just to clarify what we mean by finding the wavelengths, we're expected to convert those back to the wavelengths they would be in the air, which is pretty much the same as they would be in vacuum. In the third part of the question, we take the entire lens and immerse it in oil, and this creates a bit of a new situation because the oil has a higher index of refraction than the fluorite. That creates a slow to fast to slow transition, and this forces us to go back to first principles and figure out the wavelengths that will interfere constructively and destructively, because we never found a formula for this slow to fast to slow situation. So to start things out, we're asked to compute any visible wavelengths of light. So we're restricting ourselves to only those that land between 400 and 700 nanometers roughly, whose reflections interfere destructively when white light is incident on this fluorite layer. So there's our incoming ray coming in at right angles, and we end up with two reflections, one off of the top surface of the fluorite. And just to clarify, we're assuming that it's air out here, which would have an index of refraction of about 1. And that first reflection is phase shifted, I'll just write PS, because it's at an interface where the light is slowing down. In other words, I'm going from a lower index of refraction to a higher index of refraction. The part of the light that penetrates all the way through the fluorite to the crown glass, some of that is going to be reflected off of the crown glass. And because again, the index of refraction is increasing at that interface, the reflected wave is going to be phase shifted by the reflection. And then there's the additional possibility of a phase shift occurring because of the extra travel distance for that wave. The thickness is given to us as 89 nanometers, and the additional travel distance is twice that much because the wave has to go through the fluorite on the way down and on the way back up. In part 1, we're looking for destructive interference, and because both of these waves are phase shifted, I need my extra travel distance to undo the phase shift on the second reflection to get these waves back out of phase. Well, the first way this can happen is if the extra travel distance, 2t, is equal to half a wavelength of the light in fluorite. And that wavelength of light in the fluorite is notated as lambda prime. Solving for lambda prime, I get 4t. I can plug in my thickness of 89.0 nanometers, and I get 356 nanometers for a wavelength of light interfering destructively. Now remember, that's the wavelength of the light within the fluorite, and I need to convert back to what it would be in vacuum. Well, we know that lambda prime is the wavelength in vacuum over the index of refraction for the materials, so that's lambda over 1.43. And we multiply by 1.43, obtaining a visible wavelength of 509 nanometers. So in our reflected light, that 509 nanometer light is going to be missing. And in fact, you get partial destructive interference in a neighborhood of that 509 nanometers. And this is a good anti-reflective coating because it's basically carving out kind of in the middle of the visible spectrum, and it should make it so you get less reflection off this lens than you otherwise would. Now we're going to look for another wavelength that interferes destructively. And the next one still requires 2t to get us a half a wavelength of phase shift. And that happens if we fit in 1.5 wavelengths, or 3/2 lambda prime, in a distance of twice the thickness. So that additional integer wavelength doesn't cause any problem as long as we're left with an extra 1/2 of a wavelength to cause a phase shift by way of extra travel distance. We're going to get both of these reflections to be out of phase when they emerge from the fluorite. So before I do any calculations, I want to note that we're definitely talking about a shorter wavelength now because 1.5 wavelengths fit into twice the thickness, whereas before it was only half a wavelength. So as we look for these higher order destructive interferences, they must be shorter wavelengths. Solving for lambda prime, that's 4t over 3. So that's 4 times 89 nanometers over 3. And for lambda prime, I get 119 nanometers. Again, that's equal to the wavelength in a vacuum over the index of refraction. So taking 119 times 1.43, I get 170 nanometers for my next destructively interfering light. Now that's a wavelength shorter than the shortest visible wavelength of about 400 nanometers. So this is actually ultraviolet light, and it's not really what's been requested here because we only want the visible wavelengths. And if I continued to look for higher order destructive interferences, those wavelengths are increasingly shorter because I'm fitting more wiggles on that 2T travel distance. So I'm guaranteed that there are no more visible wavelengths of light that are going to interfere destructively through this thin film. In the second part, we're asked for any visible wavelengths of light whose reflections interfere constructively when white light is incident at right angles on this film. And again, we have a phase shift for the light at each of the reflections. So the reflections don't put the waves out of phase. If our extra travel distance doesn't mess with the phase of the second reflection, then we'll get constructive interference. And the first one happens when the extra travel distance is equal to exactly one wavelength so that it doesn't mess with the phase of that reflection. And I get lambda prime is equal to 2T. That's 178 nanometers. And again, that's the wavelength in vacuum over the index of refraction for the material. I get 255 nanometers. And that's going to be the longest wavelength of light that interferes constructively through this thin film. Because if I look at my next order constructive interference, that's when two wavelengths fit into twice the thickness of the film. In other words, I'm talking about a wavelength that's half as much. So given that this first one is ultraviolet, already beyond the visible spectrum, the second one's going to be even shorter, so it's also going to be ultraviolet. Just for completeness, I'll work out the calculation real quick. The wavelength is 89 nanometers within the fluorite, and the wavelength in a vacuum is 127 nanometers, so definitely getting shorter and definitely ultraviolet. So neither one of those is a visible wavelength, so the answer is that there are no visible wavelengths that interfere constructively through this thin film. Now in part 3, I want to know how the answers change if the lens is immersed in oil, and this oil has an index of refraction of 1.5, making it larger than the index for the fluorite. So there's my incoming light wave. There's my first reflection. There's my second reflection. And what changes is that at the first reflection, that's a transition from a slower material to a faster material. The index of refraction went down, and there's no phase shift caused by that reflection. The second reflection is still phase shifted because it's a transition from a faster material to a slower material. So to begin with, maybe I'll do the destructive interference. Because one reflection is phase shifted and the other isn't, we're going to get destructive interference if our travel distance doesn't mess with the phase of that second reflection. So that would be when the travel distance is an integer number of wavelengths within the fluorite. The first one would be when 2T is equal to lambda prime. The second time this occurs is when 2T is equal to 2 lambda prime. So all that's happened here is that I'm going to get destructive interference in the same places where I got constructive interference before I put this thing in the oil. That first wavelength, we've already done the math, is 255 nanometers, and the second one's 127 nanometers, and they just keep getting smaller. So there are no visible wavelengths of light that are going to interfere destructively once I immerse this thing in oil. What about my constructive interferences? Because one of these reflections has no phase shift and the other is phase shifted, I'll get constructive interference if my extra travel distance for the second reflection puts that reflection a half wavelength out of phase. The first time that happens is when 2T is equal to lambda prime over 2. And again, I noticed that I've done these calculations before. It's just that that was the calculation for destructive interference when the lens wasn't in oil. So 2T equals lambda prime over 2. The way that turned out, lambda was 509 nanometers. So now my 509 nanometer light is going to interfere constructively instead of destructively. Again, the next time this happens is when 2T is equal to 1.5 wavelengths, or 3/2 lambda prime. And the way that turned out was a wavelength of 170 nanometers. And again, that's ultraviolet. So basically you immerse it in oil and all the answers from the first two parts just reverse. I get only one interference that's happening in the visible spectrum, and it's a constructive interference on 509 nanometer light, exactly the same wavelength that was destructive before we put it in the oil. If you find the physics content on Zach's lab helpful, Click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.